Okay, right, so it's kind of 2 steps to what we're doing here. Number 1, you've got an image, you've got to find all the faces in the image, which means like a sort of rectangle with the faces. And then, so doing that is kind of a solved problem. It's like an old problem. Facial recognition stuff, or detection stuff has been around for a long time. So we can do that well already. So the interesting part is that when you've got this the rectangle, you take the face. The interesting new part is that you want to take that and say, okay, how happy, for example, is that face? That facial expression maybe. Okay, is everyone like roughly following so far what I'm talking about? Yeah. So historically, there's a lot of theory out there, kind of complicated theory about like there's all these different muscles, and when you use your face, like you're pulling different muscles. So there's this massive list here. So, for example, happiness is apparently action unit 6 and 12. 6 is a cheek razor. Apparently that's involving your orbicularis oculi, something. This is it's kind of complicated. You can see it this way. Okay, so we could do that, or we could just use machine learning, which is a kind of awesome new thing that's taken off in the last 10 years. So there's been rapid progress recently, especially in computer vision. So instead of coming up with all this theory and stuff, we just tell the machine like what we want it to learn, and then sort of let it work out for itself what's the best way of doing that. And yeah, the sort of the lesson of maybe the last 10 years is that you can come up with all these kind of complicated theories and like these formulas for doing stuff, but actually just letting the data speak for itself ends up working better than those like explicit theories you can come up with. Okay, but we actually need data. So what data? Anyone who's, have we got any machine learning people here? Yeah, kind of. No. So anyone who works in machine learning can probably tell you that like, the techniques is they're kind of out of the box and not too tricky. The hard bit is actually getting all the data. So what we're going to need like hundreds of faces showing different expressions. We need to like create these images and we need to label them. And there's some like publicly free like data sets out there. This thing on the right, apparently I don't really use it, but it's the Kern command data set. But you can kind of see that, so this thing was created in the lab by researchers, and there's some kind of obvious potential problems with this, at least with what we're going to try and do, which is kind of want this to work on like a picture that might. So these things are highly posed, and they're taken in like controlled conditions. It looks to me like a lot of these are kind of exaggerated as well. Like someone showing surprise is probably not actually going to pull like this face. So yeah, and also like coming back to this idea of like all this complicated theory. These are made by researchers, and it might be the researcher has some like specific theory about, okay, a smile is about this muscle here pulling and this muscle here pulling. Kind of instruct their subject, this is the right way to do the smile. We don't really want to do that because we don't know if that's actually right. So also the lighting and stuff is all really controlled there, which it wouldn't be in real life. And so here's the sort of general principle. So the data you use, it's got to kind of match the data that is going to be applied to in real life as closely as possible. So that's why we have this thing. So this is SView. It stands for static facial expressions in the wild. The in the wild bit refers to the fact that they're not like strictly controlled. They're kind of in random environments. They're taken from 54 films. And the research, the people who made this data set, they did this kind of clever thing where they went through the actual like subtitles in the films, and they found like anything associated with happiness, for example. And then they made this program that like said, okay, the frame that we reckon has lots of emotion in it. So they could quickly go through. They didn't have to watch like hours and hours of film. They could quickly find frames that were expressive. And give them labels. Okay. Does this still all make sense so far? Mm-hmm. Yeah? Okay. You can see, so there's a lot more variation in lighting and stuff. Technically, like in films, lighting is way more controlled than kind of realized, but at least it's kind of trying to be varied and natural. Also, you could maybe argue that like acting and expression isn't the same thing as the expression actually happening in real life to a real person. Especially if it's like, not a particularly good actor, or maybe it's like a comedy and more exaggerated. But at least kind of the general goal is to, in general, to the sort of natural implements and sort of actor's general goal. And also, so the main thing I think is that these were labelled by people. So these weren't labelled by the actors. It's not as if the actor like was told to smile and then they smiled. The actor was doing whatever, and then someone came along and said, "Oh, I recognise this as a smile," for example. So there's like no theory, there's no instructions. This is what the expression looks like, at least according to some people. Okay. So we're going to use machine learning. Here's a kind of overview of what that means. So we've got all these faces, and then we've got like the correct label for each face. And the goal is we want to make an algorithm. Anyone here like not know what an algorithm is? At least roughly, yeah. And this algorithm is taking in pictures of faces and it's spitting out like an expression. And we want the expression to be correct, basically. So this is a successful machine learning algorithm, and this is like a failed one. Okay, how do we do it? So we don't want like an algorithm that's frozen, like a single set of instructions. We want it to somehow look at our data and then work out what are the right rules. So like, in other words, like the algorithm has to kind of be flexible. It has to have some kind of settings that it is like using to make its decisions. And then it's going to sort of look at different settings that are going to cause it to predict in different ways. Most settings are going to be useless, like if you just choose random settings and it's going to spit out random stuff, basically. It's not going to be any better than chance guessing. But if we sort of tweak the settings in just the right way, then maybe more often than not, it will start guessing sort of the right expression. And yeah, so ideally we want to get the settings so that the predictions are always correct. But actually doing that is the sort of learning of machine learning. Okay, so we need to, so this is going to be done by a computer, so we need to be a bit more precise about what a good algorithm is. In fact, like it turns out that it's easier to sort of think about what's a bad algorithm and then try and make the algorithm as not bad as possible. So this badness, we call it the cost. So the algorithm, it makes its predictions. So like here, for example, it's saying 100% sad for this face, 100% surprise for this one. So number one is wrong, and number two, it was like very certain, and it was still wrong. It was like 100% certain this was sad. It was wrong. So that would get like a very high cost number. This is better, like they're both right, and it's only not perfect because it was only sort of 80% sure that it was a happy face here. And then this thing's perfect, so it's 100% confident about the right answers. That would be a zero cost. So what we're trying to do is we're trying to fiddle with, so this thing has some settings, we're trying to fiddle with the settings so that the cost decreases. So we could, like a first idea would be to like, why don't we just try every single combination of settings and then just pick the best one. But if there's like loads of different settings, then that's going to take too long. Like typically algorithms are going to have hundreds of settings, which means you're going to have to try like trillions of different combinations. So instead we do this. So we start with basically random settings, and then for each setting, you want to sort of work out, if we change it a little bit, is that going to make it better? And then if it does make it better, then we sort of twiddle it in that way, and then in that way the algorithm gradually gets better. And yeah, we do that repeatedly until it's like as good as we want. Yeah, this thing on the left, like it's pretty abstract, but the idea is that, so this will be for an algorithm with only two settings, and that's the cost of the top. So remember, that's like how bad the algorithm is. So we're trying to get the lowest cost possible. So you can see we're kind of like slowly tweaking the two settings there, and it's reducing the cost. Okay, yeah, a quick note on like on generalization. So the algorithm might just memorize all the pictures in the data set. So if it, certainly like if it had too many settings, it could just kind of save each picture internally. And then when you show it the pictures, it would just remember like, oh, I've seen this before, this is supposed to be happy, for example. The point is that that's kind of useless, like it wouldn't work on new data. It hasn't really learned anything. Yeah, it hasn't generalized. So how do we avoid that? So what we do is we actually split the data set in two. We call it training data and validation data. So yeah, the training data is what we're going to show the algorithm to tweak the settings and make it better. And then once we're kind of happy, we share the validation data, and that's our test of whether it's actually working properly. This is kind of a generally important principle in science, that you can just look at the data you have and you can always craft some theory around it that makes it make the right predictions. But the sort of real test is always that you look at new data that you haven't seen before. And it has to work better. And if it doesn't, then you don't really have something that works. Okay, so far I've been kind of vague about like what the algorithm is, how it works, what are these settings, how do they affect its predictions. There's actually a bunch of different things we could try, but the thing that works best is neural networks. Has anyone heard of neural networks? Show of hands? No. Yeah? No? So yeah, they're really taking off at the moment, and they're behind self-driving cars, for example, all these latest devices, all the cool stuff. Okay, so they are kind of inspired by the brain. They don't exactly follow how the brain works. For one thing, we don't really know exactly how the brain works. But basically the brain is connected by a bunch of cells called neurons, and they fire signals to each other. And where these neurons connect is called a synapse. and synapses can get stronger or weaker, and that's going to affect, when a signal goes across it, it's going to affect how it changes the neuron after. And there's a lot that's unclear, but it looks like when you learn stuff, a lot of it is to do with these synapses getting stronger, or at least changing the way they behave. So we copy this, but like on a computer, and that's what an artificial neural network is. So this is an artificial neuron. So instead of like neuron signals, we now just have like numbers or something on the computer. So we've got a bunch of numbers that come into this thing. So we've got 2, 3, minus 5 here coming into this thing. All these numbers come in, and then this artificial neuron spits out another number, which in this case is minus 25. And also, so the synapse stuff, so the strength of the synapse, we call that a weight. So here, like the 10, minus 10, and 3. These are the settings. These are the things that we like change when we are trying to make our algorithm better. Exactly what happens is really not too complicated. So see this like formula up here, right? It's multiplying each number by the weight. So 2 times 10, 3 times minus 10, minus 5 times 3. And it's adding up all those numbers. It's like combining all these numbers in that way. And it's a tiny bit more complicated, but that's basically what it does. And then a neural network, so this is just a single neuron, but an artificial neural network is again really not too complicated. We just take a bunch of these things and we glue them together. So they are organized in what we call layers. So here we've got a thing with sort of 4 layers. So this first layer, kind of wire it up to, in this case, the image. Right? So so an image is made out of pixels, right? Each pixel has like a different brightness. So each of those pixels like directly feed into an input neuron, and then those signals get passed on to the next layer using that kind of formula I just went over, and then they get passed through the network until they get out the other end. At the other end, we kind of tell, well, we assign each of these neurons on the ends to one of the things we're trying to predict. So in this case, that top neuron is like the happiness neuron. It's detecting how much happiness there is. And the idea is that like the higher the final value, so we've got all these values in this image, they get passed through the network somehow according to its settings. We get these final values, and the idea is that they are supposed to represent like how confident it is in one way. So a higher number for happy means it's pretty sure that the image is happy, for example. Okay, this is all kind of simple but also kind of complicated. So does anyone want to ask any questions about how this stuff works? Is anyone confused? Or yeah.
Sorry, you said that the pixels were going through the neurons. Is it every pixel individually would be going through it, or would it be groups of pixels?
Yeah, that's a really good question. It depends. But like for this example, you can imagine that we resize all the images to the same size. Generally, not too big, like maybe 200 by 200, for example. So that's like what, 4,000? Someone help me. 40,000. Yeah, different numbers. Each individual number goes to an individual neuron. Yeah. So you can think of this first layer of neurons like basically, yeah, every neuron gets a pixel. That's how you can think about it. Yeah.
So it's basically like when you're taking a photo. So when you use a camera and you put the sensor, it's kind of does the same thing.
Yeah.
So,
Yeah.
so what is the difference? So what is the difference? My question is, what will be the difference between these and all the machines that do the same?
So, like with a camera, that's just kind of storing the data. The difference with this thing is that it's passing it through this network, like it's doing stuff to the data. And ultimately, it's just turning it into these 7 numbers. That's the difference. Yeah. Any other questions?
So just, okay, so we're looking at that one and the smile is kind of like that.
Mhm.
If it's lopsided and I'm sort of sitting there sideways on,
Yeah.
I presume it doesn't.
That's a good question. I'll kind of cover that in a couple of slides, I think. Yeah. But if I don't answer that properly, like, ask me again.
I'll make a note.
Okay. Right. Okay, so this is like a picture of how maybe the first layer works. So, okay, so pretend we've like trained the algorithm and we've got it into a good sort of working state. It's actually making good predictions. So, why does this, we could have done like lots of different things with the image, like why does doing this specific thing work quite well? So, okay, let's look at the weights in the first layer, the strength of the synapses in the first layer, that is. So, because there's currently like 1 neuron per pixel, that also means there's like 1 strength or 1 like weight per pixel. So that's what this like second image is showing, for example. Like you could have a bunch of negative numbers and then below it like some positive numbers. And what that's actually going to do is when all those signals go through that thing, they get multiplied by the weights and added up. It's actually going to like respond positively if there's like a dark shape with a bright shape below it. So you can kind of think of these initial layers like one of these things, whatever it's called. Like there's got to be a certain shape to get through. Like if it's roughly the right shape, you can kind of squish it through, but it's not as good. Yeah, so this is just 1 neuron in the first layer, and it looks like it's kind of, for example, detecting whether the top lip is curved upwards, for example. Does that at least roughly make sense? And then the next layers, so let's think of the very next layer. So it's got access to all these neurons, like, so maybe there's a neuron that's detecting whether the top of the lip is curved upwards, and maybe there's another neuron that's detecting if the bottom lip is curved upwards. So it's got all these things, and it, like, it weights them. So for example here, both of those things are going to contribute positively to it thinking that the image has a smile, for example. And then it kind of repeats that process. So as it goes through the network, it's building up like more and more abstract concepts, in a sense. Until we get to the final layer, which, remember, like, is supposed to be representing the individual 6 or 7 expressions. So for example, for the happy neuron in the final layer, if everything's worked properly, then for example, maybe there's like a neuron for detecting a smile, and there's a neuron for detecting like if the left eye is kind of happy, and maybe there's also a neuron for detecting if they're not smiling, if they've got a frowny mouth, and that would have a negative weight on it, for example. Again, does that kind of roughly make sense? Yeah. And it also turns out when you look at human brains, they kind of work in maybe the same way. Like there's layers to the human visual cortex, and it literally goes from your eye, and like you've got an optic nerve, feeds all these signals in, it just goes backwards through the layers in the back of your brain, and we can kind of see we can kind of see that, so certain neurons respond to like lines at certain angles, like in the initial layers, and then you can also see them responding to certain shapes as you go further back. And then, like, ultimately, after a few layers, it gets confusing, basically because the concepts have gotten really abstract. So that's the idea, anyway, is that there's a lot of uncertainty about how the actual brain does it. Okay. So that was a simple artificial neural network where every neuron in the previous layer was connected to every other neuron in the next layer. There's a few reasons that might not be the best idea. Number one, like, that means there's loads and loads of connections. If you imagine you have like a few hundred neurons in each layer, then you're going to have like a few hundred times a few hundred connections between them. It's quickly going to build up to like millions of connections. They're all going to have their own settings. So making this thing learn, or even just putting images through it, is going to take a long time. And also, this comes back to the point I kind of try to make about if you've got too many settings, you can just start memorizing the image. So we want to keep the number of settings as low as we can, so that this thing generalizes well. Also, like, you can argue, okay, if these first layers are like trying to detect what is simple shapes, like is this thing curved or not, then why does it need to be connected to every single like neuron in your eye? Like, if it just wants to know, is there a curve down here? There's no reason for it to like be looking at stuff up in the top left or whatever. And also, yeah, I think this is kind of your question. So, like, at least in the previous example, if it saw a face like basically the same as Harry Potter, but with like a longer nose, so the smile was below where it was before, then you need like a whole new neuron to work out that region of the image was smiling.
Presumably you need something to work out that it's actually a face in the first place.
It does. So we're kind of assuming that. So even if you knew exactly where the face was, people's faces are different shapes. So like if you superimposed everyone's face, the stuff wouldn't line up.
They all have two eyes and nose and mouth.
Yeah. But they're in kind of they don't necessarily overlap. So it can't rely on locations of stuff. So this is part of what these fancier neural networks are about. So they don't care where stuff is, basically. Yeah, and also, so these simple ones we looked at a second ago, everything was connected to everything else. Again, like human brains don't work that way. Kind of crazy, there'd be loads of connections. So, yeah. So the solution is these things called convolutional neural networks. They kind of state the art. They're pretty cool, but also they're pretty simple. Like, in fact, they're almost simpler than the ones we just looked at. So they're like the neural networks where everything is connected to everything else. But actually, we don't let everything be connected to everything else. Like only neurons that are nearby can be connected to each other. So we just get rid of most of these connections. And also, like, so stuff isn't like anchored to a location. Once we've got some weights, pass them over the whole image. So, for example, it doesn't actually matter where a smile is, as long as there's a smile like somewhere on the face. This thing will find it. You don't need to worry too much about this, the animation, but it's not too it's not too bad. Like so, these things in the middle are the settings. It's just a bunch of numbers, normally like 9 numbers, and this thing gets passed over the whole image, and it produces some kind of transformed version of that image. Yeah. So why are we doing this? So again, like, this has way fewer settings. So previously there'd be millions, but now we've, like, at least this thing, we've only got 9 settings, which means because we don't want to use too many settings, we can now have lots more layers without like exceeding how many settings is too many.
And is the overlapping an error detection?
How do you mean overlapping?
So I can see that it's sort of scanning, but then rescanning certain lines at different points.
Yeah. So what's happening there is that each neuron in the next layer is connected to like a small but larger area in the previous layer. So it's not. You can kind of maybe think about it as error correcting, but.
Is it like you have to look at more than one pixel to see the difference? Like, so the smile, if you're trying to see sort of light below,
Yeah.
dark, you have to be able to see is the pixel below darker or not, rather than just looking at one pixel.
Yeah. So in fact, so the ones we were looking at before, they would have looked at every single pixel in the image, and that's crazy. But you can't make it so simple that it's only looking at a single thing. It needs to be comparing pixels next to each other.
Sure, yeah.
Context.
To see the changes. Any other questions about this specifically? Is everyone kind of at least very vaguely following? Because it's pretty, there's a lot of concepts on it. Yeah, it's actually not too bad. Yeah. So this is just a bit more detail on actually what happens. So, for example, if you, I'm not going to go through like why, but if you happen to have those numbers and you did that, if you applied that, so that's like a single. If you applied that thing to an image with those 9 numbers, so that image on the left turns into the image on the right, you can actually see what it's doing there. Is it's seeing where are the horizontal lines in the image? Those are coming out bright, and then everything else is like not really activating that neuron. So these things, they can detect lines, they can detect like patches of color, and then the next layer on, because the previous layer is telling it lines and things like that, you can use those concepts. So like if there's a line, if there's a horizontal line next to a vertical line, for example, then this thing can detect corners. So it's slowly building up concepts as it goes through the network.
So is it almost like using the contrast to create like a 2D wireframe of something that's really true?
Almost like using a what, sorry?
Like, so you, I mean, when you look at the image at the top, effectively what you're doing is you're looking at the contrast, producing like a line drawing rather than a shaded drawing, which they
Yeah.
can shape, is that?
Yeah.
What you're saying?
I mean, certainly that's an example. Like, so when you train one of these things, you'll find that it typically will, for example, learn this in order, because it needs to be able to see lines in order to do its job well. But there's also like a bunch of other things that it will learn that are maybe like harder to interpret. But all of them are basically this kind of thing. Yeah.
So so in that instance, for example, that particular kernel is working to expose just the horizontal lines in the image, and then presumably each sort of stage or layer in your neural network will further process that data in the way that you want to.
Yeah.
So the first layer, for example, might just get out the straight lines, pass to the next layer, and the next layer will begin to process those
Although,
lines.
so I should emphasize, like, each layer has lots of these kernels, so there'll be one that's sort of working out where the horizontal lines are in the first layer, but also in the first layer there'll be one working out like where the vertical lines are.
Sure. yet you have many different processes going on to combine
Yeah.
into your picture at the end.
Yeah. Okay, yeah. So that's, I mean, that is basically the basic idea. I mean, it also, like, every so often, you can see in this diagram, don't be too intimidated by it, but it's basically doing what I just said. Like, you got the image, it's applying a bunch of, here it's applying like 24, I think, kernels to it. So it gets like 24 transformed images here. And then it does it again. But then also, it, like, every so often, it needs to shrink it down because it needs to combine information from, at least at some point, it needs to pull together information from different locations and image. So we need to shrink stuff down until it gets to a single point. And then at the very end, there's like the simpler network we had from before where everything's connected together. There's like one of those stuck on the end. So it's doing all this transformation stuff, and then it's coming out with a bunch of values that might represent certain things, like you know, a smile or whatever, and then it's combining those with this final layer that's connected to everything. Yeah.
Just a question, maybe a bit silly. The values for happiness, sadness, and stuff are always the same, or do you determine, or do you determine which value corresponds to happiness?
So yeah, like when you set this up, you need to decide, well, I want this neuron and the final layer to be the happiest one, for example. And then when you show it the data, so you've gone through all these images and you've labeled them like this one's happy, right? You need to sort of translate that and say, okay, this one I want the first modifier.
So is the data scientist who establishes the threshold, just to say, so okay, so happiness is this, sadness is this, and then you let the machine do the rest?
Yeah.
Okay.
In fact, yeah, so we've gone through like a lot of stuff, so this, I'm just going to recap everything we've gone over. So we've got, yeah, we start with a bunch of like, faces, right, that we've labeled with the correct expressions. We split them into a training set and a validation set. So the training set, so we've also got this, so we make this neural network thing, which can pass these images through and make a prediction using like its internal settings. Right? We start off with random settings, and then we put all of the training images, all of the images in the training data, we put all those through this random sort of initial network. Right? It makes its predictions. We calculate how good they are, right? And then we work out how to tweak the settings to make them better. And we keep doing that. And then eventually we've got a good network. And we test it on the validation thing, on the validation images, which it hasn't seen up till this point. And that's like the final test to say, does this thing actually work? Does it generalize the data it hasn't seen? Okay, has anyone, so that's the final slide, at least on how this stuff works. Has anyone got any questions about the general process or specific details? Or does everyone know exactly how convolutional neural networks work?
How would we, now understanding the vague way that this works, how would we go about setting up such a system ourselves, or to go about?
I mean, practically there's all these like, free software packages out there.
Are there any particular ones that are good? Or
Yeah, the famous one is called TensorFlow.
TensorFlow.
Yeah,
Sure.
and then there's some like easy, so there's like a Python interface for that called Keras, and it's really easy. Like it's out of the box. You just say, you know, make a neural network. I want it to be convolutional and this many neurons in domains. You just make it, and then you just give it a data set. So the actual number of lines you need to code this kind of thing.
Sure.
20 lines or something, because it's all done for you.
Sure. So I'm just trying to imagine it. So say in a particular task, for example. Can you? I guess right. Okay. So say if the task is to determine whether or not there's an animal in an image.
Yeah.
How might you go about that if you?
So you need to start by making a data set.
Yeah.
So you can go on Google and get lots of pictures of animals, and then also you need like as many pictures not with animals in them. Right?
Sure. So that's like your training data.
Yeah. And then you basically just set one of these things up in Python or whatever, and you give it the data, and it takes a few minutes or hours to learn.
Sure.
That's basically it.
Oh yeah. Awesome. Thank you.
What's your question, sorry?
That was going to be similar kind of thing, how the actual practical process that you're going through, which platforms you're using to do that.
Yeah. Yeah, like I said, so personally I use this thing called Keras in Python, which just wraps around this the low-level implementation of TensorFlow.
And of course, there's lots of, I mean, every big company out there has got their own AI learning model out there.
They
There's
do,
Watson,
although they're all,
there's-
like maybe 80% of them will actually be ultimately using TensorFlow. They'll have made their own thing with their own data,
Right.
but because the calculations basically are as simple really as a outline, so there's really not much scope for doing it differently, and doing it well, like, there's only really a few ways of doing that, so it's been done well by TensorFlow, which is Google, so it's kind of always sort of people redoing that.
So I guess the complexity comes in the neurons and the number of them rather than the actual equations that each are performing. And it's just a question of tuning that over time to
Yeah,
the ones that are going to be the best output.
yeah. No.
So let's say that the neuronal network trains itself, right?
Pretty much, yeah.
Okay, so is the data scientist the one who sets up that frequency on so does it refresh themselves?
That's a really good question. So that's like, that's actually kind of a common misconception about machine learning, that it doesn't need to be like always sat there, always learning new lessons. You can just like prepare, this is what is done half the time, you prepare this big data set for it to learn. And you show it the data set, and then it sits down, takes a few hours, it learns from it. But once it's learned, it's kind of done, and then you use it.
It's just because I'm thinking not really into video analytics, was mostly in like natural language processing. Language is something fluid, and for instance, you get memes, you get new expressions as well. So
Yeah.
so it's something that sometimes can take a long time. Sometimes it can
Yeah,
something
so
viral. So
it comes down to the use case. Like if the thing you're trying to model is changing over time quite fast, then for example you can either just keep gathering data and every so often you retrain the whole thing, or there's actually ways of just retraining it a little bit, so you don't have to do the whole process again. You just show it new stuff and learn about the new stuff.
So when you say the Google owns TensorFlow, I mean the big one that I know about was AlphaZero doing chess. That
Oh,
a similar scenario took place there with the data set and spreading the information.
It was using convolutional neural networks, but like in a more complicated setup where it wasn't as if it didn't have a labeled data set. It didn't have like a bunch of games that had been played, and like maybe it's not as if someone went through a bunch of games and said this was a good game, this was a bad game. It was playing games against itself. It's called, what is it called? I can't remember the term, but basically you make two neural networks just compete against each other. But the actual the actual sort of learning core was a convolutional neural network. So it was like two convolutional neural networks sort of fighting each other to try and get better.
Right.
But yeah, it would take a while to explain properly. I think how specifically. Yeah, but it was it would have been TensorFlow.